Hi, this lecture is close on the heels of the last lecture, Connectedness 3. So, what we are going to talk about is the characterization of connected spaces in terms of continuous functions. This is a very important tool. It's unfortunate it's not very much emphasized. In fact, I would say it's not even emphasized in many books and by teachers. See, dealing with many students have problem with connectedness, especially connected subsets, because if you look at standard textbooks, the so-called disconnection for a connected subset, for a subset, okay, to be not connected, you have to think of a disconnection, and it has a lot of very complicated conditions you have to check for. Okay, that puts off a lot of students. And second thing is, they don't have any concrete examples. Whereas in last few lectures we had already given a lot of concrete examples. In the first lecture we looked at abstract examples, and in the second lecture we looked at examples in R and R2, and today we are going to talk about characterization of connectedness in terms of continuous functions. And it's very, very powerful tool. All the results you want to prove about connected spaces can be used by this in a very, very easy way. Believe me, you are going to witness that. Okay. And just before I start, there is a prerequisite, some two basic facts about subspace topology. You will be surprised. Subspace topology is given very scant attention in the courses. But there are two facts. One fact, both the facts you will use throughout your life or throughout your career in mathematics. Very rarely you stop to think whether I proved it rigorously at some time in my life. Okay. And the first one you will immediately recognize, yes, I know that. And second one you may not have even thought about. But both are easy. And the second thing is actually universal mapping property for subspace topology, which I would explain in my fourth lecture on generating topologies. But if you have not seen it, don't bother. I am going to prove it without any jargon in a direct way. Okay, stay with me. We will get to the business. So we are going to start with the preliminary on subspace topology. So let x tau x be a topological space, A be a subset. Then we know what is the subspace topology. I denote by tau A, which is given by the collection of sets of the form U intersection A, where U is open in X. Okay. The first fact is, as I said, all of you know. Suppose F is continuous from X to Y. And suppose A is a non-empty subset, it could even be empty, a subset of X. Then I can restrict F to A, right? You know what it is. F restricted to A at X is F of X, as you can see here. Yeah, right. Now let me denote that function by G, the restriction. Then I have function G from A tau A to Y tau Y. So what is G of A? G of A is nothing other than F of A for A in A, right? Okay, so I can ask whether G is continuous, and I know all of you immediately say yes, it is. Okay, have you ever proved it? Has it been given as an exercise after you define subspace topology? I'm not very sure. Okay, if you are done, good, well and good. Otherwise, let's go through. So to prove G is continuous, what should I do? I should start with a V. Let me just check whether I started the thing. Yeah, right. So let V be open in Y, then I have to say G inverse Y. This is open in X. This is what I have to check. So let us look at the definition. So when X belongs to G inverse V, okay, remember our mantra, if and only if Gx belongs to V. Yeah, where is X? X is in A. When does this happen? What is Fx? That is Fx is in V. You follow that? Yeah. So what do you think I have done? So G inverse of V is by definition set of all. Let me look at A in A, so that G of A is in V. But this is same as saying A in A. What is G of A? It is F of A is in V, right? But this is same as saying set of all X in X, so that Fx is in V and set of all x is in A. See, it has to satisfy two conditions. A must be in A and FA must be in V. Therefore, it's same as saying FA must be in V and A must be in A, right? But this object is F inverse of V intersection with A. Yeah? Do you follow that? If you are not sure, please pause, review and proceed. Now suppose F is continuous, right? Therefore this is open, this is in tau x. Therefore this whole thing is in tau A. That means G inverse of V is in tau A. That means G is continuous. So F continuous implies G from A tau A to Y tau Y is continuous. Okay, pause, review, proceed. Now I want to look at the second fact. Now let F be a continuous function from x to y to y. Okay, this is just a function. Be a function, right? Assume f of x is contained in B, where B is a subset of y. So let us have a picture. This is my x and this is my y and this is my B. So my fx always, any x immaterial of x, it always lands in B. Now can you think of what is the question I want to ask? Yeah? Therefore now I have a function g from the set x to the set B, where g of x is f of x. Yeah? Now therefore I can think of g as a function from the topological space x tau x to B tau B, where tau B is a subspace topology. Yeah. Now my question is, the assertion I want to say is the following. Okay, this is a fact. This is actually universal mapping property for subspace topology. What does it say? F from x tau x to y tau y, where f of x is contained in B, is continuous if and only if, okay, g from x tau x to B tau B is continuous. Okay, proof is easy. Let me quickly go through the proof. So let us assume f is continuous. So I have to prove g is continuous. So let w be in tau B. If w is in tau B, that means there exists a v in tau y, so that w is v intersection B. Is that clear? So I have to prove g inverse of w is in tau x, is open in x, right? So let us look at what is g inverse of w. This is set of all x in x, so that gx is in w. Yeah, right? Okay, but notice that this is same as saying set of all x in x, so that what is gx? Gx is, sorry, w is v intersection B. Are you following? Yeah. But what is this? This set of all x in x, so that gx is fx. Fx is in V. Are you following? Fx, if you want, don't worry, gx is in w. Let me scrap this. This is in w. But this is same as saying set of all x in x, so that fx is in V. Because w is v intersection B. Do you understand this, why this happens? Because remember, let us look at, this is my B. So this is my B, this may be my V, this is B, and this is W. You understand? But what do I know about this? What I know is, if I take X, every X lands only in B, therefore it is here. Okay, right? So this is nothing other than F inverse of B. This object is F inverse of B. Since F is continuous, this belongs to tau X. Therefore what I have shown is G inverse of W is F inverse of B, where W is in tau B and W is V intersection B. Okay, this is set theory, right? Please pause, review, proceed. Now let's assume G is continuous. I want to know that F is continuous. It's essentially a set theoretic thing, but once you have done this, after that you will be free. To show F is continuous, what should I do? So F is from map from X tau X to Y tau Y. So let me start with a V in tau X. So I have to check F inverse of V, whether it is in tau X, right? Let's look at that. What is F inverse of V? It is set of all X in X so that Fx belong to V. Yeah, but remember, Fx always lies in B. Therefore this is set of all X in X so that Fx belong to V, but certainly it belongs to B. Do you understand this? Right. Yeah, but notice that for each X, this is same as X in capital X. This is Gx belong to V intersection B. Now V intersection B is open in B. Yeah, therefore this is G inverse of V intersection B, and this is open in B, and G is continuous, therefore this is open in X, therefore F inverse B is open in X. So pause, review, proceed. Go through the proof. You may not have seen such a thing, so take some time. I deliberately chose G instead of using the same F so that you should think of them as different functions, okay, because their domains are different. Okay, domain of F, domain of G are all different. And in the second case, in the first case, again the same thing. Okay, please understand. Right, this is it. Please go through it, make sure you understand. Now we are going to prove a characterization. Let me call it a theorem. It's a very powerful characterization and simple characterization. Of connectedness. So what does it deal with is, let us look at X tau X space. Okay, let us look at the set plus or minus 1 as a subset of R. Okay, this is a subset of R with the usual topology. Therefore the topology, subspace topology on plus or minus 1 is a discrete topology. Okay, keep all these things in mind. I am going to say X tau X is connected if and only if every continuous function F from X tau X to R such that F of X is contained in plus or minus 1 is a constant. So you can also think of this F as a function from X tau X to the set plus or minus 1. Notice that F from X tau X to R such that fx is contained in plus or minus 1, that is continuous if and only if f from x tau x to plus or minus 1 with the subspace topology is continuous. That's what we just now saw. That's fact number 2. Do you understand that? Please go through it. Okay, these kind of subtle things teachers don't want to push. Okay, so notice that by fact 2 f from x tau x to r with f of x contained in plus or minus 1 is continuous if only if f from x tau x to plus or minus 1 with the subspace topology, namely discrete topology, because that's a subspace topology, is continuous. Okay, yeah, right. Now let's prove it. Okay, proof. Suppose x is connected. Okay, let f from x tau x to r be continuous and f of x is contained in plus or minus 1. Yeah, then I want to say f is a constant, right? Okay, so let either 1 or minus 1 should be in f of x, right? Because it takes values here, and if f is a function, therefore this, okay, with our loss of generality, assume 1 belongs to f of x. Then what do I want to do? To prove f is a constant, I want to prove fx equal to 1 for all x in x. This is what we want to prove. Do you follow that? Very good. Yeah, right. Now let's look at the set 1. Okay, call this V. This is a subset of plus or minus 1, and this is discrete topology. Therefore this is open. Okay, where? In this space, right? Therefore f inverse of V is open because f is continuous. Oh, yeah, all right, f is continuous, therefore it's open. Now to notice that, okay, 1 belongs to f of x. That means, okay, this is not empty. Okay, and further notice that since this is discrete topology, V is also closed. So V is both open and closed. Therefore this set f inverse of V is open, it's non-empty, it's also closed because V is closed. But x is connected. Therefore what do I know? F inverse of V must be all of x. That means give me any x, in x, fx belong to V. But what is V? Singleton 1. That means for all x in x, fx is 1. That means f is a constant. Okay, so what have we shown? If x is connected, if f is a continuous function from x tau x to r, which takes values inside the set plus or minus 1, then f must be a constant, right? Now I want to prove the converse. Okay, so let us prove the converse. Converse. What is the converse? Okay, many of you will have problem with formulating converse because logic is not well understood. Okay, so what did we prove? What was the claim? The claim was x tau x is connected if only if every continuous function. Therefore what should be the hypothesis? Assume x tau x is with the following property. What is the property? You give me any continuous function f from x tau x to r such that fx is contained in plus or minus 1, then f must be a constant. That is the property of x tau x. Then what is that I have to prove? X is connected. Have you understood? Okay, very good. Suppose x is not connected. Okay, then I want to prove a function, okay, which is not a constant. That function is easy. How many of you have gone through my lecture on continuity? There I would have proved the following. Suppose x is a set and okay, a is a subset of this, then let f equal to chi of a. That is a characteristic function of a. Then I have proved chi a is continuous if and only if a is both open and closed, where chi a is 1 if x belong to a, 0 otherwise. How many of you remember this? If you remember this, now can you think of a function f? So what do I have to do? Prove to I have to arrive at a contradiction, right? So I have to think of a continuous function from f from x to r, which takes values only in plus or minus 1, but not a constant. That means it takes both the values plus 1 and minus 1, right? And since it's not connected, what do I know? If it's not connected, that means there is a subset u, or call it a, which is both open and closed. You understand that? Since x is not connected, there exists a, okay, subset of x, so that a is both open and closed, right? Therefore, if I take the characteristic function of a, it's okay, it's a function from where to where? X of x to r. What values it takes? 0 and 1, but the subspace topology on 0 and 1 is discrete. If you don't like it, I can simply modify. What will I do? I'll define f of x equal to 1 if x is in a, and equal to minus 1 if x is not in a. Then okay, f is continuous. From where to where? F is from x of x to r, so that f of x is equal to plus or minus 1. Why it is equal to plus or minus 1? Because a is non-empty and a is not equal to x. Therefore, there exists one x which is not in a. That okay. Therefore, fx must be minus 1 for that. Therefore, f assumes both the values. And a is non-empty. Therefore, there exists at least one x. Therefore, fx equal to 1. 1 is a value. Minus 1 is also a value. Do you follow that? Okay. So, why this is continuous? To prove this continuous, I have to look at, okay. Now remember, this is a function. I can think of this as a function from x of x to plus or minus 1 alone with the subspace topology. Therefore, what are all the possible sets here? Empty set, singleton 1, singleton minus 1, or plus or minus 1. Okay. So I have to check the inverse images are open, right? Now what will be f inverse of empty set? That will be empty. What will be f inverse of plus or minus 1? That will be x. What will be f inverse of 1? That is very a. What is f inverse of minus 1? That is x minus a. And this is open, this is open, this is open, and since a is closed, this is also open. Therefore, I have proved f is continuous. Right? Do you understand that? So what do you think I have proved? I have proved that if x of x has a following property, namely any continuous function from x of x to r with f of x contained in plus or minus 1 is a constant. That should imply x is connected. Have I proved it? Yes. Why? If it's not connected, start with a set which is both open and closed. It's not empty set, it's not equal. Then essentially the characteristic function of a will satisfy this condition, except it takes values in 0 and 1. Simply modify that. Okay. So pause, review, proceed. Have you understood? Yeah? Okay. let us apply this result, right? So we will say applications of this thing. Suppose A, B are connected subsets. Subset topology space x of x. Assume that A intersection B is not empty. Then I want to say A union B is connected. This is the first application. So notice that in R, if I take something like -1 to 0, 1 to 2, this is connected, this is connected. Maybe you could take closed interval because that's all we have proved. Okay, right? But the A union B is not connected because A union B is not an interval, therefore I know it's not connected. You understand that? So I have to assume I said A intersection B is not empty, but I wrote A intersection B. Follow that? Yeah. So how do I do that? To prove F is continuous, okay? To show A union B is connected, what should I do? I will use my characterization. Let F be a continuous function from A union B to R, so that F of A union B is contained in plus or minus 1. Right? You understand? Okay. Right. Assume that. See, if one of them is empty, A union B will be one of the non-sets. Right? If A is empty, A union B will be B. If B is empty, A union B will be A. If both are empty, of course it's empty. You understand? And do you understand empty set is connected? Okay. Okay. Right. So now let us look at this. Suppose this is a continuous function. Then what do you have to prove? I have to prove F is a constant. Anyway, I said A intersection B is non-empty, right? Therefore, neither A can be empty nor B can be empty. I'm sorry. Okay. Okay. Sorry. Yeah. Yeah. So this condition implies A is not empty and B is also not empty. Yeah. Right. Very good. Now let me use the first fact about subspace topology. Since F is continuous from A union B to R, right? So restriction of F to A is continuous. And what do I know about A? A is connected. Therefore, F must be a constant on A. You follow that? Because A is connected. Say F equal to 1 on A. Do you follow that? Very good. But for a similar reason, B is connected, that implies F must be a constant on B also. I say F must be 1 on A because there is an X which is common to A intersection B. Right? Therefore, for any B, F of B must be equal to F of X. It's a constant, right? So fix one point, namely X in B, which is also in A. But what is Fx? Since X is in A, Fx is 1. Therefore, what I have proved? For every B in B, F of B is 1. That means F is constant 1 on A, constant 1 on B, therefore it's constant 1 on A union B. Have you understood? Forget this rectangle. Okay, this is nothing to do with the triangle. You follow that? So F is a constant. If F is a constant on B, fix a point. Okay. Therefore, for any arbitrary X, or arbitrary B, Fb must be equal to Fx. But X is in A, therefore Fx is 1. That means for every B, this implies F is equal to 1 on A union B. That is, F is a constant. That means A union B is connected. Have you understood? So pause, review, proceed. As an application 2 is actually an application of 1 also. In the last lecture, do you remember, if I take two intersecting lines in R2, these are intersecting lines, okay, then this is my set A, or call it S, okay, S is connected subset of R2. Why? Because we proved any line in R2 is connected. This we proved in the last lecture. So therefore this is a line connected, this is a line connected. So this call it A, this is B, but A intersection B is non-empty, they will be this point. Right? Therefore A union B is connected, but A union B is this pair of intersecting lines. Do you understand? So in R2 we have seen lot of conic sections, either degenerate, non-degenerate, and checked connectedness, non-connectedness. Yeah, right. Now let's look at more. Let me look at a third example. It's a generalization of the law. Suppose I have a topology space x of x, right, and suppose A are connected subsets. For each I in I, A is connected. Okay, assume that there exists, okay, for all I and j, A intersection Aj is not empty. Then I claim A equal to union Ai, I and I is connected. The proof is again easy. Let f be a function to R so that f of A is contained in plus or minus 1. Right? Now fix a j in I and an x in aj. Let us look at fx. Call it 1 without loss of generality. Right? This is just fixed x. Right? Since Aij is connected, I know f of Aj is singleton 1. It must be a constant. Right? Now I claim f is a, now notice that y, see, let me again go slow, restrict f to Aj and therefore Aj to R. Okay, then f of Aj is again contained in plus or minus 1. Okay, now by fact 1, okay, f is a function from A to R and Aj is a subset of A. Therefore when I restrict f to Aj with subspace topology, what should happen? Since Aj is connected, it must be a constant, so call that constant as 1. You follow that? Yeah. So we are using the fact 1, right? Okay. Now let's look at similarly f at Ai for any I in I, this is a constant, right? But remember there exists an x, call it xi, which is common to Aj intersection Ai, because for each I and j, this Aj intersection Ai is not constant. You follow that? Yeah. Therefore for any x in Ai, f of x must be equal to f of xi, but xi is in Ai, therefore f of xi is 1. Therefore for every x in Ai, f of x is 1, but this is true for all I. Therefore if x belongs to union Ai, then x belongs to some Ai, okay, but then f of x is 1. therefore f is constant. Yeah, so I want to prove f from A to R is a constant if f of A is contained in plus or minus 1. Do you think I have shown? Start with any x in U, that means there is an I such that x belong to AI. Yeah, because A is union AI. But then f of x must be equal to f of xi, because if AI is connected, therefore f restricted to AI to plus or minus 1 is a constant, and xi belong to AI, therefore f of x must be f of AI, but xi is in AI. Okay, this xi is where? In AI intersection aj. On aj f is a constant 1, therefore it's 1. So what do you think I have proved? F is constant 1 on all of A, therefore this. If you again, you may want to look at an example. Okay, suppose I have this. Okay, so let me look at, okay, an R2, let me look at AN equal to, or even if you call it AR, where R is in Q. Okay, and R lies between Q intersection 0 1. Okay, this is 0, this is 1. And what is AR? AR is this line. Okay, AR is set of all xy so that x equal to R. Okay, this is x equal to R line. So at each R I am producing this. Okay, and let B equal to the x-axis. Why I will take all? Okay, right? So what are these lines? The lines are at x equal to R. These are all x equal to R, where R is a rational number, and this is my B. B is x-axis, that is y equal to 0. Okay, and this is a line, therefore it passes through both ways. Now let us look at this set A, which is AR union B. Is this connected? It is connected because each AR is a line, therefore it is connected. Okay, but remember, when R and S are different, AR and AS have no intersection. You understand? But what happens is, okay, this B intersects with each AR, right? For every R, AR intersection B is not empty, namely it contains the point R comma 0. You follow that? Therefore A is connected. So how will I prove that? Again the same thing. Let f be in A to R, f of A equal to contained in plus or minus 1. Now restrict f to B, that is x-axis. Since this is connected, f is a constant, say 1. Right? Now let's look at, then I want to say f is 1 on all of A. This is the claim. Now start with any point R comma Y where this is in AR, right? Now the comma R comma 0, this is a point common to AR intersection B. Yeah, and now when I restrict f to AR, since AR is connected, this is a constant. Okay, but the point R comma 0 is in AR, therefore f at any R comma Y should be f at R comma 0. But R comma 0 is a point in B, therefore it's 1. Therefore what do you think I have proved? F of Ry is 1. And for which R? For every R in Q. Right? Therefore I have shown f is a constant, namely 1 on all of A. Therefore a special case is the following. Something similar is what is called comb space. What is that? Exactly the same thing. At each 1 by n, you look at this line. So an equal to set of x y in R2, so that x equal to 1 by n and 0 less than equal to y less than equal to 1. So this is y equal to 1, and this is 1, this is half, this is 1/3, okay, and this is not included. Yeah, so and my b is set of all x comma y, so that 0 less than equal to x less than equal to 1 and y equal to 0. That is the part of this x-axis. This is my b. This is my b. These are my ans. Okay, and this point is not here. This is not in the space set. Okay, so what I have, a equal to union an, n union union b. This is connected. So we have shown that comb space is connected. Why this is called comb? Can you believe this? So this looks like a comb, right? Like that. Okay, this looks like a comb, that's why it's called comb space. Okay, before I stop, let me give one more example. You will see the power. This is 4th or 5th application. Suppose x tau is a topological space, and suppose A is a connected subset. Let B be a subset between A and A closure, right? Then I want to say B is connected. You should look at the traditional proof in standard textbooks for this. Now you compare that proof with the proof which I am going to give here. To show f is connected, what should I show? Let f be any continuous function from B to R, so that f of B is contained in plus or minus 1. So to show f is constant, right? Now if A is a subset of B, therefore when I restrict f to A, since A is connected, f is a constant on A. Say f equal to 1 on, yeah, okay. Then what do I want to do? I want to prove f is constant on B, because I want to show B is connected, right? Now let's look at the picture. So this is my A is the interior, and this is my A closure, and B may be in between. Okay, now start with any x in B. Now remember, B is a subset of A closure, and those of you who have gone through my lectures on closed sets, you know A closure is characterized. A closure is nothing other than set of adherent points. See, what is adherent point? When I say x is an adherent point, if every open set U containing x, the U intersection A is not empty. That's the definition of adherent point, right? Now start with an x in B. B is contained in A closure, therefore x is an adherent point of A. you follow that? Therefore, if x is in B and B is contained in A closure, implies x is an adherent point of A, right? Okay, right. So what do I want to prove? I want to prove f of x is a constant. Remember, A is already a subset of B and here it's a constant 1. Therefore, what should I prove? I should prove f of x equal to 1. Do you understand this? Very good. Right. How am I going to prove that? So I have to use is an adherent point. So how will I do that? Yeah. So let U be any open set with x's in U. Right? Now U intersection A is non-empty. You follow that? Very good. Okay. See, this is an open set. Where? This is an open set in X. Right? Therefore, U intersection B is also not empty. Because U intersection A is non-empty. A is a subset of B. Therefore, U intersection B is not empty. Do you follow that? Okay. Now, since X is an adherent point, okay, there exists an A in U intersection A. Right? That is, it is in U intersection B. Do you follow that? Therefore, A is a point where in U as well as in B, and A is also in A. Please pay attention. Okay, this is something like your U, this is my A, okay, this is my X, this is my A. Alright, very good. Now, what do I know about FA? FA is 1. Right? Okay. So what do you think I can do? I'm sorry. Let me approach this. Okay. Forget this. Okay. I want to prove F is 1 on B. Right? Suppose not. Let's assume f equal to minus 1 on, okay, fx equal to minus 1. Okay, there exists x in B, so that fx equal to minus 1. Okay, now x is in B, B is contained in A closure, therefore x is an adherent point. Right, very good. Now let's look at fx equal to minus 1, therefore let's look at minus 1 as this is open where in plus or minus 1, right? And f is continuous from where? B to plus or minus 1, right? Therefore f inverse of minus 1 is an open set where in B, and x belong to this because fx is minus 1. Do you follow that? Now we are through. Now since this is an open set, call this as U, and x is an adherent point of A, therefore U intersection A is not empty. So there exists A in U intersection A, which is contained in U intersection B. Yeah, you follow that? But A belong to A belong to U, that implies f of A is 1. What is U? When does A belong to U? If only f of A is minus 1. Therefore f of A is minus 1. but a belong to a, that implies f of a is plus 1. So this is a contradiction. Why it's a contradiction? Because I wanted to say f is 1 on b. If not, there is an x so that fx is minus 1, right? There is x in b so that fx is minus 1. Then what did we do? Then we looked at the inverse image of minus 1 under f. That must be an open set in b, right? Okay, now what do I know? X is an adherent point of a, right? Therefore u intersection b, okay, u intersection a must be not empty. Therefore there exists an a in u as well as a in a. Since a is in u, f of a is minus 1, a is in a, f of a plus 1. That's a contradiction. Yeah, therefore we have shown that, okay, if a is connected and a sub b in a closure, then b is connected. In particular, a closure is connected, right? So as a specific example, let us look at the comb space. Comb space, what did it have? an union b and this union n. What are ans? Suppose this 1 by n, this is my an, okay, and this even though I have drawn, you should remind this is not there. Okay, this is something like this is x equal to 0, it's not there, right? So all these things are going to be there. And this is my b. Okay, now call this as a. There is union an, union b, n in n. We know this is connected. What is a closure? A closure will be exactly the same thing, but now this is also included. These are the ans, okay, and this is also included. Therefore this is connected. But most important thing is, let us look at a set C which is 1 0 comma 1 union an union b. This is a subset of a closure. Yeah, so what do you see? Again, let me look at a picture. A1, A half, an, okay, and this is my b, these are my an, and only this point is included. Okay, this is my c, this is connected. Do you follow that? You may think it looks like a single piece. It's not. Yeah, that's a very interesting thing. Yeah, please go through it. I hope you enjoyed this lecture. We will come back, okay, with some more applications of this characterization. Pause, review, proceed. Please go through this, and in the characterization continuous, please visit again. Make sure that you understand, because many times the inverse images, subspace, etc., people are not very clear. Just go through it. I given a very elementary basic proof, okay, no terminologies, no kind of jargon. Go through the proof, understand, and then see how we use it repeatedly. Okay, the proof is very interesting. Okay, we will come back with some more applications in the next lecture. Okay, till then, take care, stay safe.